Hello there, and welcome again to this tutorial series of deep learning and machine learning technologies. In this video, we are going to look at different components of an ANN, which is artificial neural network. Then we are going to look at what is the structure of an ANN, what makes it so reliable, and then we will try to understand what goes inside a single neuron. Basically, we are going to dissect a whole ANN architecture, and we will try to understand what goes inside a single neuron, and using all these concepts, we will try to create a sample ANN model which will try to predict the house price for us. So let's start on this journey. Let's understand the overall structure of a neural network. By this time, it must be very clear to you that a neural network or a dense neural network is a combination of a lot of neurons connected together in a particular fashion. And how do we connect all these neurons will depend on what type of use case we are dealing with. For example, here we have this neural network in front of us, and this here, since we are taking the input at this input layer, this I will just highlight this for you. Since all of these three neurons are taking input, so that's why we call this as an input layer. Now after this input layer, we will usually have a hidden layer. So these neurons are called hidden layer because it's sandwiched between the output layer and an input layer. And this single neuron here is called as our output layer. Now why I have taken only one neuron in an output layer and only three neurons in an input layer will depend on the type of data you are dealing with. For example, if you have four inputs which will point to one output, if you are trying to predict the house price or house rent, for that you will need four variables: the area of the house, how many number of rooms are there in a house, and what is the number of washrooms in that house. We are using three variables to predict one output, which is the price of the house. That's how we decide how many number of neurons will be in input layer and how many number of neurons will be in output layer. I will explain this in more detail in further slides, but for the time being, let's just assume that number of neurons in an input layer and number of neurons in an output layer is very important to decide when we are trying to create a neural network. The number of neurons in hidden layer will usually depend on hit and trial, what combination works best for us. Now let's understand what goes inside a single neuron. Let's suppose I have a single neuron here, and by definition a single neuron is a computational unit that simulates the behavior of a biological neuron. So basically what scientists have done, they have tried to clone the same neuron which we have in our brain and try to put in machine learning and deep learning technologies. So I have deleted all the network architecture here. Here we are trying to understand only one neuron and what goes inside a single neuron. So let's understand what are the basic components of this neuron. So one neuron will have one input. Apart from this input, we will also have weight. So this weight will decide how much influence each input will have on this neuron's output. I will explain this in more detail through an equation, but let's first understand all the components. So after this weight, we have bias. So bias will allow the activation function to be shifted left or right. If you don't know how and what activation function works, don't worry, I'm going to explain you also. But I have created a separate video of how the activation function is used in neural networks. If you want or you are interested in details of activation functions, you can watch through that. Now, based on these three factors, the output will be calculated after applying the activation function on top of it. For example, if input here is, suppose I'm giving an input 10 and weight here is 1, bias also here is 1. So what we will do, we will calculate the x here. So x is nothing but the summation of all the input to it. For here we have only one input, so it would be 10 into, what is the weight here? 1. So this will decide how much influence this input will have on the output of this neuron. That's why it's weight. Then we will apply a bias here, which is 1. So output here is 10 into 1, which is 10 plus 1, which is equal to 11. Now this is our x here. So x here is equal to 11. On this x, we will apply an activation function. So what does this activation function tells? If the x is less than 0 or equal to 0, the output is x. sorry 0, and if this x is greater than 0, the output is 1. It's very important to understand that if after applying the activation function on this x here, if the output is 0, that means this neuron is not activated. If the output here is 1, that means this neuron is activated. I will repeat this again for you. Suppose this is a single neuron. Let me first delete all of this. Suppose we have a single neuron here, and on this neuron we have this input. So suppose the input we are having 10, and the weight which we have designed or decided is 1 here, and the bias is 1. So we will, to calculate the x here, we will do the summation of all of the inputs here. So we have only one input here. So what we will do, we will do 10 into 1, which is our input into weight. Here is our weight, plus we will do the bias. So bias is 1. So this will give us 11. So x here is equal to 11. Now on top of this x, we will apply the activation function. Now what this, just for the simplicity, I have taken a very simple activation function here. What this activation function does, if this x is less than equal to 0, output is 0. And if this x is greater than 0, in which case it is indeed 11, so our output would be 1. So this neuron, according to this input, is activated. Because the output is 1, that means activated. If the output is 0, that means it's not activated. Now let me give you a scenario in which it is not activated. Suppose input here is minus 10. Weight still here is 1, and bias still here is 1. So to calculate x here, what we will do, the input is 10, we will multiply it through the weight, and then we will sum the bias, which is 1. Okay, let me just delete. I have written the bias there, so it would be 1. So which is minus 10 into 1, which would be minus 10 plus 1, which is equal to minus 9. Perfect. Now x is equal to minus 9. Now on top of this minus 9, we will apply the activation function. So f of x is less than equal to 0, so our output here would be 0. That means this neuron is not activated at all. Very simple to understand. Now similarly, if I have multiple inputs here, for example, I have input 1 here. Let's suppose I have one more input and I have one more input here. So here I am supplying it 1, here I am supplying it 2, here I am supplying it 3. So we have 3 inputs to this neural network, sorry, not neural network, the neuron here, and I have here, let's call this x. So x here would be equal to summation of all the inputs into all the weights. I mean, let's suppose weight here is 2, and let's suppose bias here is again 2, plus we will have the bias added here. So in this case, if at all I have to calculate all the input, this is how I'm going to do it. So input 1 is how much? This, let's start from here, 2. So 2 multiplied by the weight 2. Again I have input 1, so 1 multiplied by the weight, which we have 2 here, 2. Again 3 is the input, so plus 3 multiplied by the weight 2. And at the end we will add the bias, which is 2 here. So how much this is equal to? 2 into 2, which is, it's just a mess right now, so let me write it here. 2 into 2 is 4, 1 into 2 is 2, and here again 3 into 2 is 6, plus the bias here. So this is equal to 4, 10, 12 plus 2, which is equal to 14. So here x is equal to 14. Now on this 14 here, we will apply the equation fx. So f of 14 here will be equal to how much? It will be equal to 1. That means this neuron will be activated. Super easy to understand, isn't it? Let me summarize the 3 scenarios which we looked at. First, we looked at how this neuron will be activated based on the input 10. Weight was 1 and the bias was also 1. In this case, neuron was activated because applying the summation function, which is wi into input of I plus bias. Applying this equation, we calculated the x here, which is equal to 11. So f of 11 equal to 1. In this case, our neuron was activated. Instead of input 10, if I take the input -1, in this case, our f of, -1 into 1, which is -1 plus 1, which is equal to minus of 8. So minus of 8, in this case, output would be 0. So our neuron won't be activated. Apart from this, we also looked at how we can handle multiple inputs. So once we have multiple inputs into a single neuron, of course, we are going to use this equation here. So idea is that we always calculate the x in here using this equation, and on top of this x, we always apply the activation function to get the output. Now this activation function can be of any type. For simplicity, I've just taken here a normal fx is equal to 0 when x is less than 0 and fx is equal to 1 when x is greater than 0. We will have sigmoid, ReLU, tanh, different kinds of activation function. So I have already created a separate video on this. You can watch through that. So this is what happens inside a single neuron. Now that we know what goes inside a single neuron, let's combine a lot of neurons and create a sample architecture. So this is a sample architecture for you. So it has all the neurons. So we have our input layer here. So this is our input layer. This is our output layer. Here input layer, because we are trying to take all the inputs using these neurons. And why we are calling this output layer? Because we are trying to calculate or get the output using this neuron. And between input layer and output layer, we have a sandwiched layer, which is nothing but our hidden layer. Perfect. And if we want to apply the activation functions, so we will be applying on these hidden layer neurons. So suppose this layer of neurons, I'm applying sigmoid function. On this layer, I will be applying ReLU. On this layer, I will again apply ReLU. Usually on input layer, we don't apply any sort of activation function because input layer is meant to take all the inputs. That's it. It's very simple. And here using on this output neuron, we are just trying to get the output. Very simple to understand, isn't it? Now using this architecture, we will try to create a sample neural network model which will predict the house price. Now let's understand the type of data which we are going to use. So this is the sample data or a sample structure of data which we are going to use. Suppose our data has these 4 columns, which is the area of the house. Then we have how many floors in the house, whether that house has parking or not, whether that house is having a garden or not, and whether this house is having a waterfront or not. Very easy to understand. Using these 5 features, we are trying to predict what would be the price of the house. So we have a historical data. Suppose we have, suppose 1 million data like this. We have all these 4 records for 1 million house prices. So using this data, we can create an ML model which can predict. If you want to predict the house price in future, you supply these 4 details into this model and it will tell you what would be the price of this house. Easy to understand. Now let's understand how we are going to design the network. So since this house data has 4, sorry, not 4, it's 5, 1, 2, 3, 4, and 5. It has 5 important features, which is area, floor, parking, garden, and waterfront. So at input layer, we will be having 5 neurons. So it would be 1, 2, 3, 4, and 5. These are the 5 neurons through which we are trying to take the input. Using this input, we will be applying all sorts of different activation function on these neurons. And an output layer, we are just trying to get the price. We will usually represent the output with Y. This is so simple. This is the architecture which we are going to build through Python. For simplicity, I am using an Anaconda and Jupyter notebook here. The kernel here is of Python 3. And so let's start. Let me import all the necessary libraries. I will be using pandas, sklearn library, and keras models. Also, I will be using sklearn metrics. So let's import all of it. So here we have pandas, which will be used to load the data frame, and we will be using text train split from a sklearn library, and we will be using min-max scaler to scale the data into minimum and maximum value. Of course, NumPy, the most usual library. Then we will be using sequential and dense and activation to create our model. And as an optimizer, we are using Adam here since it's a regression network. Regression means we are trying to predict something numerical value. And for metrics, we are trying to use a sklearn matrix. These are all most used libraries in machine learning. Let me just run all of it, and that's it. Now let me try to load the data. So we will be using data frames from pandas pd.load.csv. Since our data is in CSV form, we will be using that file. So it should be pd.read.csv. Perfect. Read.csv, and that's this. We will supply the file name here. So our file name is price.csv. So basically this CSV file contains all the data about house and its prices. Let me just run and show you what this data have. So df.head, let's display 5 rows. So this is the sample data which we are having. What we are trying to do here is, just let me highlight it here. Okay, so we are trying to predict this price here. We are going to create an artificial neural network. If we will supply these values, bedrooms, bathrooms, square foot living area, floors, waterfront, and other columns, if we will supply these features to this network, it will predict the price for us. Super amazing, isn't it? Super easy. Let me just repeat it once again for you. Here, the thing we are going to predict is the price of the house, which is y. So y is equal to price. And to predict price, we are going to use these many feature columns here, like washroom, square foot living area, floors, waterfront, view. It's basically a lot of data. The example in which I gave you, just for the simplicity, I took only 5 columns there, which was like area of the house, then it has garden or not, then it has waterfront or not. Just for the simplicity, I have given the example of only 5 features. Here we have taken more than 5 features. Let me just delete this mess. Perfect. And let me delete this one as well. Perfect. Let me just print all the columns what I have. So df dot columns. Okay, what's this? Oh, there is one spelling mistake here. Amazing. So these are all the columns which I'm having: ID, date, price, number of bedrooms, bathrooms, a square foot living area, waterfront, basement area, on which year it's been built. So these are the, I would say it's somewhere around 15 or 16 columns which I'm having. We are not going to need all of these columns to predict the price. For the simplicity, I'm going to drop some of the columns. So let me make a list, column to drop. What are the columns I'm going to drop? Let me drop ID. You see ID here, it's of no use to us. Then after ID, we are going to drop the zip code. Where is the zip code? Let me just copy it. Can you see zip code here? Yeah, there it is. I'll be, just for the simplicity, I'm deleting any any columns which will pose any threat to us. So we will be also deleting let long, although we can use latitude and longitude, but just for the simplicity, let's make it as simple as possible. Latitude, then we will be also deleting longitude. And I don't want the complexities to handle the date in this video, so let me delete the date as well. Perfect. So what I will do, I will just use the drop method. So df dot drop, what I want to drop, I will supply it in this method. So I want to drop the drop columns. So perfect. And I will just run this. Oh, what is this? Not found. Oh, I have to supply the access. Silly mistake. I will have to supply the access as well. So access is equal to 1. So it has dropped all these columns here. So let me just again show the data to you. df.head. Perfect. Now it does not have ID and it does not have any other extra columns. Let me just print the columns again for you. So df dot columns. You see, now it does not have these columns like ID, zip code, lat long, and date. Perfect. Now we can use this data further. Let me just drop from here price as well. Since we are going to predict this price, let me drop this price from here as well, and let me create two variables, which is x is equal to df dot. So this x will not contain price. That means this is the feature which we are going to use to predict the price. So df dot drop. What do I want to drop from here? I want to drop the price column, which is nothing but this. So I'm dropping the price column. I should also specify the axis here. Axis is equal to 1. Perfect. And what I'm going to predict? Y. So inside y, what should contain? So y should be df dot price. It should contain price. So let me just summarize this line once again for you, what I am doing here. So inside this here, if you will see, okay, just it's a mess again here. Let me clean it. Okay. So x here is nothing but we are everything inside this data frame, we are deleting the price and supplying it to x. So x contains all the features which we are going to use to predict the price, and all the price is stored inside y here. Isn't it easy to understand? Perfect. Let me just delete this. All right. We need a new cell here. Let's add a couple of cells. Perfect. So I have x and y here. In next step, what I will try to do, I will try to create the x train and y train using the train test split method. So let me just copy my code, okay, and paste it here. So we have x train, x test, y train, and y test. We are going to use train test split, and instead of we are using small y here, let me make it small y here as well, just for the simplicity. So let's just run this. Oh, it's a mistake here. df.price. Perfect. So we have our x train, x test, y train, and y test. These are just basically, we can use these from by default train test split method, which I have imported here. There you go, train test split method. Basically here what we are trying to do, whatever the data we have, we are trying to split it into train category and test category, so that once we create our model, we should also be able to tell how much accuracy does this data set has. If we have 100 records in our data set, we are keeping 30 records aside to test whether this model is giving some sort of accuracy to us or not. Perfect. In next step, we will try to scale the data between a min and max value. So let's use this function. Let's create a variable called a scalar, and we will be using min max scalar. Min max scalar, perfect. So I'm using min max scalar to scale down the data. Basically, what I'm trying to do here, every value in this data set, I'm trying to map it between 0 and 1. This just helps in training the model. So our x train and x test, this is how I'm going to transform it. So x train will be a scalar dot fit dot transforms. Inside this I'm supplying x train, then again I'm supplying x test. So let's just transform this. So once I have transformed it, let me just print the values inside x train and y train, just to give you an idea what this data has. So print x train, what is the max value in x train, and print what is the max value in mean value basically in x train. Sorry, I think I announced x train a couple of times. Sorry for that. So minimum value inside x train is 0 and maximum value is 1. Perfect. So now our data has been transformed or fitted between a minimum value of 0 and maximum value of 1. Perfect. Now let me print the x train shape. So here is my x train. It's always easy to copy. X train dot shape. Let me just run it. So we have these many records and we have these many features. It simply means that let me just write this or highlight this for you. So we have this 1, 5, 1, 2, 9 and 15. That means we have 15 features and we have these many records in our dataset. So once we design our neural network, these 15 features will be taken as an input from the input layer. So as an input neurons, we will be having 15 neurons, 1, 2, 3 up to 15. So we'll be having 50 neurons in input layer. That's why knowing the shape is important. And how do we get this 15? Once we know the shape of our training data set. And these 15, I would say these 15 features are nothing but the same features which we have extracted from here, earlier one. Let me exit it from here. So you see, if we count all of them, they will point to 15 minus price. So if you minus price and count all of the columns, it will go to 15. Perfect. So now we are clear on the input feature and we are clear on the output feature as well. Now let me design the input layer. So let me just create this code from here and there it is. So model is equal to sequential. This is the sequential which I'm using from Keras. So model.add input layer. So inside input layer, I am trying to have 50 neurons since it's a first layer. So first layer is always the input layer. And first layer, I am creating a dense neural network of 50 neurons. Which 50 neuron? It's same as this. Perfect. So this one input layer is created. Then we will create a hidden layer. If you remember, I have shown you how you can create a hidden layer. In not create as in create, how hidden layer is present between input layer and output layer. So here we have our hidden layer. So model. So this is the actual model which we are going to create. So first layer is this, which is input layer. Second layer is 10 neurons with an activation layer of ReLU. Again, one more hidden layer. So we can add as many hidden layers as we want, depending on, basically it's a hit and trial. If these three layers works with 10 neurons in each layer, then it's well and good. Otherwise, if it's not working, then we need to have a couple of more layers. It's basically hit and trial. So this is the hidden layer. Now we will have an output layer. Let me just copy it from there and there we go. So model.add dense layer. This is our output layer. Only one layer is the output layer. Let me just summarize it once again for you. Here inside this, I am just adding all the input, not adding as in adding. I am creating 15 neurons which will take the input with an activation layer, activation function of ReLU. After that, whatever the input I have taken, I am creating a dense neural network of 10 neurons, 10 neurons, 10 neurons in each layer. Then at last, I am creating a single neuron because we are trying to get the output from a single neuron. Since it's a regression network, we will need only one neuron to give us the output. So model.add dense layer. Then at the end, we will compile the model. We will compile the model using the Adam and loss we will supply MSEs because it's a regression model. It's pretty obvious. All right, that's it. Let me just run all of them if I have missed something. Perfect, no error at all. Lucky me. Now we will just fit the model.fit. Wait a second, why I am typing so much? Let me just copy it from there. It will just save a lot of time. So what I'm trying to do, I'm trying to fit the model using this train data and using this train values with a validation data set of test values, which we already split in, upside here. We have already tested X train, X test, Y train and Y test. Perfect. So this is the training data. These are the values of testing data, and we want to train our model with 400. Let me just make it 50 so that it happens quickly. So epochs is basically how many iterations you want to go through one data. It's as simple as that. And batch size is how in one iteration how many data you want to go or how many records you want to go. It's like that. Let me just run it. So that's how pretty amazing. It's running quite fast. Perfect. The model is ready. Now once my model is ready, let me try to predict what is the accuracy of our model. Let me just copy my earlier code and there it is. So this here on top of our model, this model, I am supplying the X-test data. So this X-test data, it's the same data which we have separated in the state of trend test split, and we are supplying this data on this model to know whether how much accuracy does this created model has. So let me just run it. Not bad. So we have MAES score as this one, MSES score, RMSES score, not bad. Basically, MAE is mean absolute error and MSE is mean a squared error. RMSE is a square root error, mean a square root error. It's both are like measurement of error in using different context. Awesome. So our model is ready. Let me just supply a sample data to this model. Although we have tested our model here, let me just try to predict house price for a single house. So this is how I'm going to do it. So let me just take a single value. So let me just name the variable A, and let's take the value from X-test itself. Just to show you how you can use this created model to predict the house price. So X-test of 0. That means we are taking only one element. So let me just print A for you. So this is the values which we are going to use to predict the house price. Basically, these values are nothing but same values which we are using here. They are just transformed into values of max and min of 0 and 1, of course. So what we will do in next step, we will try to put it inside a variable test, which is of numpy array. So np dot array. I will put this A inside this test, and now let's try to predict. So we predict value will be equal to what is our model name. So our model name is this. We can name this model as per our liking in future, but for the time being and for simplicity, I have named just model. What do we want to do on this model? We want to predict. With what value we want to predict? We want to predict using this test value. Perfect. Let's just run it. Oh, what is this error? Oh, it's the problem with the shape. What we will do, it should be inside an array. It just takes array of values to predict. Let me just run it again. Amazing. So it has predicted 1 out of 1 value. Let me just print this value. So this is the predicted house price for us. Amazing. Here we have taken only one value. We can supply multiple values inside this test, and this predict value will return an array of predicted values. Similarly, we have done here inside model.predict, we have supplied xtest. Xtest is nothing but it's an array of features on which we are going to predict the prediction. Let me just run it again and show you what's inside prediction. So if at all I print the prediction here, so can we add a cell downside? Yes. So if I show what's inside prediction, you see it's an array of predicted values. These predicted values are nothing but the price. Amazing. Congratulations on making this far in this video. Now let me summarize the contents what we looked at. So we looked at how we can create a basic ANN architecture and what goes inside an ANN. We also looked at and we understood what goes inside a single neuron. And then we applied all of these concepts to create a simple ANN to predict a house price. You can apply these concepts to create your own ANN architecture and try to create your own new machine learning models on the data which you have. So if you have learned something in this video, press the like button. This is it for this current video. Now see you in next video. Till then, bye bye.